So let's take a look at the sync circuit, and that's on this same page, and it's in the upper left-hand corner. Remember, inputs are on the left, outputs are on the right. So if we look in the upper left-hand corner, here's where the two sync wires come in, the two sync signals, and one is vertical sync, clearly labeled, and one is horizontal sync. So the vertical sync comes in here past a Zener diode, which, again, I'm sorry, I wish I could tell you what these are all for, but the Zener diode basically makes certain that that voltage never exceeds 5 volts. And it goes into this integrated circuit here, and this is a type 7486, 74HC86. It's actually called an exclusive OR gate. Digital electronics, gosh, Rudy, I wish I had more time, but there's no way in the TechFest I can explain digital electronics to you. This is not exactly a sync amplifier. It's more of a sync processor circuit. And this integrated circuit is just a real inexpensive 25, 30 cent digital integrated circuit. Runs off of 5 volts. Happens to be this integrated circuit right here, which under normal circumstances is virtually 100% reliable under normal circumstances. But you know what I did the first day of the class. And what I did the first day of the class, if you recall, was in discharging the second anode, I had the clip lead attached to the screwdriver on one end, and the other end, which I mistakenly thought was grounded, was actually connected to the horizontal sync input of the monitor. So I lost horizontal sync, and you all saw how I had no horizontal sync. Well, look, here's the horizontal sync input, and it goes right into pin 2 of that integrated circuit. Golly gee whiz, what do you think I might have blown? You think it could be the chip, the 5-volt IC that I just put 20,000 volts into? I'd say there's a pretty good chance that I blew that chip, and that's why I don't have horizontal sync. So if I had such a problem, and I didn't know anything about digital electronics, what I would say is, gee, I have a horizontal sync problem, where does it go? Well, it comes in here. Why don't we just try replacing anything that touches the horizontal sync? So that might be the thing that's bad, and I would replace it. Now, on the schematic, you see that there are 4 of these symbols. They are actually all in that same package. It's what's known as a quad, meaning 4, exclusive OR gate. These are all one device. It's all that one package. So when I change the one package, I've really changed the entire sync circuit. Yes, I did change the vertical at the same time, didn't I? Because vertical sync comes into the same part. But okay, so what? I can't get inside the integrated circuit to fix it on the inside. It's a 15-cent part. I take it out. I stick in a new one. The whole repair takes 4 minutes and 37 seconds. So, that's all there is to it. Does that make sense? I mean, if you don't know anything about electronics, you can just kind of look at it function by function. And you can say to yourself, that function isn't working. Why don't I just try changing the parts that are in that function, that have something to do with that function? Honestly, sync failures are not particularly common in most monitors. However, and this is kind of an important thing on the Cortec monitor. In the Cortec monitor, it has every monitor has its own unique little failures, these little idiosyncrasies, and once you learn them, man, you can go right to them. You have Cristal monitors that are blowing horizontal output transistors, which we'll look at in the next segment, and you replace the horizontal output transistor, and you always replace C609. Little tricks like that. I'll cover that one. Don't worry about it. And so this one also has a common problem that I want to point out to you. Let's go back to the schematic diagram, shall we? This integrated circuit that I just showed you, the 7486, actually works off of 5 volts. Most of these digital ICs do, and the vast majority do. And that 5 volts comes in pin 14. It's the corner pin, the power pin of the integrated circuit. It's really standard. Again, I wish I had more time. Well, let's see where that comes from. And if we follow that wire back, just a second. Hang on, Frank. Hang on. That was a rhetorical question. It wasn't even a question. Here we go. Let's follow it back, see where it came from. And where it comes from is the 6.3 volt power supply that I mentioned to you before, the one that powers the heater. Right? So we have this 6.3 volts DC. And actually, when I first looked at this schematic and first looked at this monitor, I said to myself, Gee, there's 6.3 volts. That must be for the heater, because remember I mentioned about 20 times that the heater works off of 6.3 volts. But I also asked myself the question, why the heck would they make it DC? It's only a heater. It works off of AC in almost every monitor in the world. Why would they want to make it DC? Let's follow this up. Follow the wire from the 6.3 volts up, 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 up. At the first connection here, the first node, as it's called, N-O-D-E, hang a right, and you can see it clearly says heater. And it goes up to the heater, goes up to the connector here, which goes up to the heater. So we know that that's definitely the heater voltage. So I said, okay, well, that goes to the heater. Why is it DC? Go back up to that node that we were just at, and keep going north. Keep going up, 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 up. Hang a left, and we see that it goes through a resistor, fairly low ohms, just 47 ohms, and to this Zener diode. Well, a Zener diode is a voltage regulator diode, and the voltage there will stay at exactly 5 volts, which is what this chip needs to operate. In other words, what we did was we needed 5 volts for this chip, and it's the only thing on the whole board that needs 5 volts. So instead of making a whole separate 5-volt power supply, they took the 6.3 volts that they're already making for the heater, and they made a DC instead, run it through a resistor to cut it down because 6.3 volts is too much, and that Zener pegs it at 5 or 5.1 and keeps the voltage at 5 volts, which is what that chip needs. So that explains to me why they made it DC. That way they can make it do two things, power the heater and power this little sync processing circuit at the same time. Well, the problem is down here. Sorry, the symptom is bad horizontal sync. And just like this one is doing, bad horizontal sync. And you can check this sync amplifier, the 7486, all day or replace it. It doesn't fix the problem. The real problem is in the power supply. Experienced technicians know that when circuits are acting strangely in some bizarre way, the first thing you really want to do is see if you have good power going to it, if the power that powers it is good. If the power supply has a problem with it, that explains why the circuit isn't working. There's really nothing wrong with the circuit. You're giving it bad power. We have an expression in electronics, garbage in, garbage out. When you have a garbage input, like a bad power supply, then the circuit gives you garbage out. It doesn't work. Well, the problem is this, and what you want to put in your notes is this. Bad horizontal sync, replace C123. What happens is that filter capacitor fails, and it fails often. When that filter capacitor fails, it allows ripple into this supply. So that voltage is jumping up and down. And that jumping up and down voltage, that ripple, affects the way the sync amplifier works. Now, it can even cause a dim picture because in many monitors, when it goes out of horizontal sync, the monitor kind of shuts itself down because it doesn't exactly shut itself down, but it kind of diminishes the output of the CRT in some cases because it's not synchronized and it just doesn't know what to do. The thing is this, that what's interesting about this is this. That power supply that I just talked about, that 5-volt power supply, powers that whole integrated circuit, which, as you saw, is both the vertical and the horizontal sync both together. Why is it that it just makes the horizontal sync go bad? If the power supply is bad to both of them, why is it not rolling vertically? Remember, that's the symptom of bad vertical sync. The picture rolls vertically one way or the other. Horizontal sync is the scramble weirdness. Why doesn't it affect the vertical as well? And the reason it doesn't is real interesting, and I mentioned it to you before. The power supply is synchronized to the flyback transformer. Look at the schematic diagram in the power supply, which we just looked at. Right at the bottom, see where it says flyback transformer locking? That's kind of an Asian way to say synchronization. Locking, they meant sync, but locking could be the same thing. It locks it in phase so that it's going at the same frequency and phase as the horizontal circuit. That's kind of important for reasons that I'm not going to get into. But that's the little loop I showed you, or at least I tried to show you earlier, but now I can because the light's better. That's just this. See this wire that's just wrapped around the core? It's a 1/2 of a turn, isn't it? This is a transformer secondary. It's wound around the core of the flyback transformer, which is this thing. It's a secondary winding made of 1/2 of a turn. It'll pick up a fraction of a volt. That might even be close to a volt, actually. And then that goes to this connector right here, which you can see is right in the power supply. That's the connector that says flyback transformer locking. So since the power supply is synchronized to the horizontal circuit, when we have this failure, the horizontal circuit is the thing that reacts to it because the ripple is at the same frequency as the horizontal frequency, so the horizontal sync just doesn't know what's going on. It's real confused. Should it sync on the sync pulse or should it sync on this ripple? It just doesn't know which to sync on. But since the vertical sync is only looking for 60 hertz, something that's 31,000 hertz, it won't even see it. It's only looking at 60 cycles per second. Okay. So that's really all I'm going to discuss about the sync amplifiers. In the rare case that you have a sync problem, look at the schematic diagram. Whatever the sync goes into, check the parts in that section. One of the cool things that you'll see about schematic diagrams in modern monitors in general, this is really a neat trick. One of the things you're going to have trouble with when you first start working on monitors is figuring out which parts do what. Which is the power supply circuit? Which is the video circuit? Which parts are horizontal and so on? In a well-drawn modern monitor, they have a really cool method of showing you what part is what. I'm so grateful for this. As long as we're talking about the sync circuit, let's go back there. Look at the sync circuit here. Notice that all the parts start with the number 200. R204, C201, R205, C202. Everybody with me on that? Go down and look at the power supply. These are all the number 100s. See, they're all the number 100s. If you go to the other page that you have, that is the other Seiju page, and it's clearly the video because you see the CRT in the upper right-hand corner. Notice that all the parts in this section here, every single one that you look at here, has the same number. They're all the 900s. Look at them. They're all the 900, aren't they? Yes. They're all, scared myself for a second there. They're all the 900s. Therefore, when you have a problem, it's simply a matter of checking all the parts with that particular number in general. In other words, if you have a power supply problem, I can say to you, look, it's one of them 100s. Change every capacitor that starts with the number 100 or whatever. And so that makes your job real easy. Is everybody with me on the concept there? It's really cool. That way we're not wasting our time checking the windshield wipers, right? If I have a power supply problem, that's a number 100. All the 900s, 200s, 300s, those are all windshield wipers. That ain't my problem. Whatever my problem is, it's in that circuit. So that's kind of a cool thing. Now, this very last segment that we're going through, the next hour and a half here, is really important. Like, all the stuff that we've done in the first 2 days is kind of leading up to all of this stuff, which is power supply, vertical deflection, and horizontal deflection. Let's start talking about the vertical circuit, the vertical deflection. We have lots of vertical deflection failures. I see them all the time. See them in the casinos, see them in airports all the time. I go to an airport, I'm on the road a lot, and the display that shows the gates and the times, invariably, the one that's my flight is collapsed to a horizontal line, and that's it. I have at least a half a dozen photographs that I've taken going through airports all over the world, Russia, Italy, O'Hare, every place, where I've just said, hey, look at that, vertical deflection failure, click. I just take a picture of it just for the heck of it. And it's really, really common. How many of you have seen loss of vertical deflection, just a horizontal line on the screen? Okay. Other loss of vertical deflection or other vertical deflection failures are where the image just doesn't fill the screen fully. Where you have total catastrophic loss of vertical deflection, you just have a horizontal line on the screen. In some other cases, you have some deflection, but it doesn't fill the screen. In some cases, it's squished at the bottom and normal at the top. In some cases, the thing's squished at the top and normal at the bottom, or the whole picture's just squished. Sometimes you see where the top is squished and literally folded over at the top, where on the top of the screen you see a real bright area and the image is kind of upside down and backwards on the top. It's called vertical fold over. These are any kind of distortion in the vertical direction. We're looking at vertical deflection failure of some sort. Well, the easiest way for us to begin to understand vertical deflection is to look at it in the form of a block diagram, as you see on the top of the page. A block diagram is a way that you can take a look at the different sections, the different functions of the monitor, without really looking at at the actual circuitry itself. We're just looking at the different functions. It's really referred to as a functional block diagram. The vertical deflection circuit begins with that vertical sync signal that comes from the computer board. That happens at the end of every field, telling it to do the retrace sequence. Then that vertical sync signal goes into an integrated circuit on the board known as the vertical oscillator, O-S-C-I-L-L-A-T-O-R, a vertical oscillator. An oscillator is an integrated circuit that generates AC. You give it a DC power supply, and that's where that 12-volt power supply is used that I mentioned earlier. You give it a DC power supply, and what comes out of the oscillator is the 60 hertz, the 60 cycles per second. That, remember, is our vertical frequency. We refresh at 60 cycles per second typically. It can vary a little bit, but typically it's 60 hertz. So this is where that 60 hertz is born. And in fact, if you have a monitor that does have a vertical hold control, which is not all of them, they don't all have vertical hold controls, you may find it also labeled vertical frequency in some monitors, as that's really what you're doing. When you're adjusting the vertical hold control, you're adjusting the frequency of the oscillator. So depending on where you have that control, the potentiometer set, you might be able to adjust it to 50 hertz, 55, 60, 65, 70. You kind of get it somewhere in the ballpark, and the sync signal comes along and locks it in place so that it's exactly the correct frequency and exactly the correct phase, P-H-A-S-E, phase. Phase is timing. You don't really have to know this, but phase is timing. Like, for example, if you think about a bunch of Army guys marching together, hop, 2, 3, 4. They're all in phase. They're all doing the same thing at the same time. They're all in phase. If they're just walking over to the PX to pick up something, to eat, then they're all walking at different speeds. They're out of phase. So what the sync signal does is it comes in and locks that oscillator so it's exactly 60 hertz or 60.001 or 60.05 or whatever it's really supposed to be exactly, and so that it is in the correct phase so that the scanning starts at the top of the screen and ends at the bottom, doesn't start in the middle and come back up, so that it's exactly one field full of raster lines. If you do not have sync, the oscillator does oscillate at its own frequency, whatever you've set with the vertical hold pot, if it exists, or whatever it's going at. So you don't actually have to have sync to make it oscillate, but the sync slightly adjusts it so that it's at the correct frequency. And you can kind of see this if you have a monitor that's rolling. As you adjust the vertical hold potentiometer, you start to see it roll up, and when it gets close, you'll notice it snaps in place, doesn't it? It kind of goes, lock, and then it locks in place. That's when you get it within the window of correctability, I guess you might say, so that the sync can adjust it. Well, this is really reliable. I've never replaced a vertical oscillator. Ray, oscillator failure ever? Twice in 35 years? Yeah. Okay. You'll never see vertical oscillator failure, probably. In fact, the only time I saw vertical oscillator failure was when we caused the problem. Someone had a monitor chassis, and he fired it up half off the monitor so that the metal frame of the monitor was touching the bottom of the board. Obviously not a normal failure. We took out more than the oscillator in that case, too, believe me. It was pretty nasty. But we fixed it. Hey, look, it's only parts. If you have to change every part on it, you can fix it, can't you? We can narrow it down by not changing power supply parts when we have vertical deflection failures, but you can fix anything if you can replace all the parts. Well, anyway, the output of the oscillator is real precise. Boy, this thing is beautiful. It's precise. The picture is locked in place. It's great, but it's real weak. We cannot use this to drive the deflection coil in the yoke. Let's keep some perspective here. Remember what this circuit is going to eventually do is drive the deflection coil in the yoke to make the beam move up and down. Well, this is real precise, but it's really weak. There's no way that it can drive the deflection coil in the yoke. That takes about 50 volts or so to give you full deflection from the top of the screen to the bottom of the screen, and this is not that. And it's real low current as well. So it has to be amplified. So it goes into the next stage. It's just an amplifier stage called the vertical drive stage. And all that just does is just boosts it up. It just boosts it up in current and probably voltage as well, so that it's, I've never really paid much attention to it, because since if it doesn't fail, I don't care about it. But that's what it's for. Now, these things are actually together in one integrated circuit. This is actually one integrated circuit that has both the oscillator and the drive. It's just a regular dual inline package IC, nothing special about it. Happens to be this one right here. Oops, sorry. Thank you. Thank you for. It happens to be this integrated circuit right here, a real common integrated circuit. There's a bunch of different ones of this. This one happens to be a TDA 9102, but there's dozens and dozens of different integrated circuits that have the same function. But I guess I just did, huh? It's all good, know what I'm saying? All right, so anyway, the output of this thing, though, is still not powerful enough to drive the deflection coil in the yoke. It has to go through one more stage, the vertical output stage. And where the vertical oscillator and driver is extremely reliable, and you'll probably never see that fail, this is a real common failure item. This is Ichiban, numero uno, number one, El Primero failure that we see in the vertical deflection circuit is the output device, because the vertical output chip will be driving the vertical deflection coil that's in the deflection yoke. So it's an output. Outputs fail the most for the 10,000th time. And so since it works really hard driving that coil, which requires a fair amount of current, it's the thing that really fails quite often. When you have just a flat line on the screen, just a straight line, the first thing you suspect is that the vertical output chip has failed, because it's really, really a super common failure. I will tell you now, though, that it's been my experience that if you have any vertical deflection at all, maybe it's only this big, it doesn't fill the screen totally, the chip itself is good. In my experience, it's been a catastrophic failure or it's working. Go, no go. Ray? Go, no go?
Go, no go unless they're using output transistors.
Oh, yeah, okay. You're talking about the U3000. Yeah. Okay. In general, pay no attention to the man behind the curtain for the moment. But he's right, of course. He's absolutely right. But in general, I mean, that's it. If you have some deflection, the chip itself is really working. And if you don't have any, you suspect that the chip is bad. I'm going to show you how you're going to verify that in just a second. Well, that vertical output integrated circuit is really easy to identify because it looks more or less the same in almost every monitor. First of all, the vertical output chip will always be mounted on a heatsink. It'll always be mounted on a heatsink. This one's quite large, actually, in comparison to most of them. And in fact, let me just pull off this dynamic focus board here. There's a little board here on the Cortec. This little board right here, it's called the dynamic focus board. It does have a nasty problem. Before I forget, this has nothing to do with vertical. It does have a really nasty problem. There's a diode on here that fails all the time. It causes you to have black jail bars on the left-hand side of the screen, typically. And you look all over and you go, where is that? I can't find it. And it's hiding underneath this capacitor right here. That's a real common failure, that diode D904. It's a high-speed diode, and I can't really take the time to discuss high-speed diodes, but that's a super common failure in a Cortec monitor. I've seen it cause jail bars on the left-hand side, or dark on the left-hand side of the screen, and bright on the right-hand side. Has anybody else seen a different symptom on that? What have you seen?
Same thing, but it usually burns up pretty good.
Yeah, it burns up good. But it burns up good, but it's like this in the monitor. So you spend 2 hours looking for burned parts on the monitor. Well, I'm exaggerating. You spend 5 minutes looking for burned parts on the monitor. You don't see any. This is what happened to me. I don't see anything bad. Call up David Capron. I say, David, I got jail bars. I've replaced a bunch of capacitors, which is usually what it is. What is it? He said, it's C904 on the dynamic focus board. I go to the dynamic focus board, and I'm looking all over, and I don't see D904 anywhere. And I call him back, and I go, tell me again where that is. It says on that little dynamic focus board. It's underneath the blue capacitor. Oh, sorry. Yeah, there it is. With a ton of silicon on top of it. Yeah, silicone, actually. So there it is. So that's a real common problem on these monitors. But now that's what's known as the modified TO220 package. That transistor, that device looks like a transistor in what's known as the TO220 package. But if you look at it carefully, it has 5 legs. Or 6 legs or something. I think 6. There's 4 sticking out the front. There's, I think, 2 or 3 underneath that you don't see. 3. So it has 7 legs altogether. It will either look like that, or it's what's known as in a single inline package, or SIP for short. Single inline package. This is from Ceramics monitor. Very common part when you want to have. So this will also be mounted on the heat sink. So it's really, you can't miss the vertical output chip. It's always in either the modified TO220 package, as I just showed you, or this single inline package. Some of them are a little shorter than others. Some are longer, but they always look like this. Okay, so that's the vertical output chip, which you really, really suspect is bad. When you have a horizontal line on the screen, which is total loss of vertical deflection, of course, first thing, of course, we know it's not the power supply, the horizontal, the video, it's none of that. We know it has to be something in the vertical circuit. And that's the first thing you suspect. Now, it's really important to know something about the way electric current flows and the way circuits work. In order to have complete circuits, in order to have these circuits work, they kind of have to have 4 things. You need to have some kind of a source of power. Let's just call it a battery for the moment. You need to have a way to get the power from the source to whatever's going to be using the power, which we refer to as the load. Let's just call it a light bulb. So we have a battery and a light bulb. And very importantly, you have to have a way to get the electric current back from whatever's using the juice, which we call the load, back to the source. And the electric current, according to conventional current theory and the way the schematic is drawn, kind of flows like that. Well, if we look at what we have, if we look at what we have here, and forgive me for being so abbreviated there, not enough time. The vertical output chip is the source of our vertical drive. I mean, that's the thing that's going to drive the yoke. And these are the brown and yellow wires. Remember I said that we have brown, yellow or green, yellow is the color for the vertical pair. So let's call that the yellow wire. So that's the source path that carries the current from the source, which is the chip, to the deflection coil. And then we have like the brown wire here that has to go to our return path, which is ground. Our return path is ground. Typically, that's true of most electronic circuits. Not all. That the current comes out of the power supply, or whatever is supplying the current, goes through a deflection coil or a light bulb or whatever, and it has to end up at ground. But, very, 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 very important in a monitor, this output will never be or rarely be connected directly to ground. I hate to say never in electronics because you never know. Some designs kind of surprise you. But it's not connected directly to ground. It goes through a capacitor first. Very important to know about this capacitor. What this capacitor does is it does not allow DC to go through. It only allows AC to go through. This capacitor is our return path, but it's not a direct path to ground. It is what we refer to as an AC return. The only thing that goes through that capacitor is the 60 hertz, the 60 cycles per second. What comes out of here is some DC and some AC. We don't want the DC part to go to ground. Capacitors have a very interesting electrical property. Capacitors will block DC. DC does not go through them, but a capacitor will pass alternating current right through it. This capacitor is extremely critical. It's the AC return for the yoke all of the yoke current, all of the current that flows through the yoke that makes the beam move up and down has to go through that capacitor. And you should know the value of that capacitor. Typical value is 2200 microfarads, 25 or 35 volts DC, depending on the design. Now, you may see it even as low as 1,000 microfarads. In some earlier designs, that was 1,000 microfarads at about 25 or 35 volts DC. But in most of the stuff now that you see now, it's 2,200 microfarads, 25 volts. It could even be 3,300, but typically 2,200 is pretty common. The reason I'm pointing it out is this is one of the common failure points in monitors. When you have a problem with vertical deflection, where you have some vertical deflection, but it doesn't fill the screen from the top to the bottom, you are almost invariably looking at bad electrolytic capacitor or capacitors somewhere. If you have some deflection, chances are pretty good the chip is good, and that you have a bad capacitor. And one of the things that kind of proves that to you is you often see it fail over a period of time. That is to say, you get to the machine and the picture shrunk a little bit. So you say, well, there's a vertical size potentiometer on the remote adjustments board, so you just crank up the vertical size and it fills the screen. Beautiful, you're done. Close the machine up, you're done. 2 weeks later, you look at that machine again. Yeah, it's machine 25 and bank 36. Wow, look at that thing. It's big. It's little again. Well, I know right where the pot is. Cool. Open it up, crank it up, pot, the thing's full. 2 weeks later, same thing. Oh, wow, well, let me just do it again. You crank it up and oops, it's all the way at maximum. And then over a period of weeks, you watch it get smaller and smaller and smaller and smaller and smaller. And eventually it starts to compress and fold over and do weird stuff like that. You're really looking at bad capacitors, and that's one of the bad boys right there, the 2200 microfarad. So typically it's pretty easy to spot, even if you are unfamiliar with the monitor. And I do this all the time. I work on lots of weird oddball monitors all around the world. I mean, you know, when I'm going to Italy or Germany, I'm probably not looking at the same monitors that we're looking at here. It's easy to spot this thing. Let me try to pull this remote focus board off here. Hang on. Even without a schematic. No, we'll look at the schematic in just a second, and I'll show you. But here's the vertical. Oops. There's the vertical output integrated circuit. We're looking for a 2200 microfarad capacitor that will be either near the integrated circuit or maybe near the yoke connector itself. The yoke connector itself happens to be right here in this case. Well, you look around, well, a 2200 microfarad capacitor is pretty big. It's got to be that one. And when I look at it, sure enough, 2200 microfarads, 35 volts, I guess not 25. That's it. I mean, that's got to be it. It just has to be it. And you would just change it. You would just say, look, I've got some distortion in the vertical direction. Oh, just change it. I wouldn't even bother testing it. You've got to be a little careful about testing capacitors. Capacitors can test perfectly okay with a capacitor meter. For example, this Fluke meter has a capacitor tester on it that measures the number of microfarads in the capacitor. And again, I'm sorry, I wish we could spend an hour or two on capacitors, but we can't. It has a capacitor tester. It's not very reliable. There are a couple of different things that can fail on capacitors. One is it can lose microfarads, but the other is that its ESR, equivalent series resistance, I'm sorry, I can't discuss this in great detail, might have increased. It's really important to have an ESR meter, in my opinion. This thing's a really great tool. It's $179, called a Capacitor Wizard. This even works in circuit very often, depending on what the nature of the failure is, to help find bad capacitors. But and I can't take any real time to discuss this. It's a great tool, but quite frankly, my best friend is a big-ass bag of capacitors, of new replacement capacitors. I didn't bring it with me, but I have a giant bag at home that I usually carry with me that is this bag, same bag as this, completely stuffed full, like Santa's bag full of toys, completely stuffed full of capacitors. And it's cost $300, that's all. $300 for every capacitor, for a year's supply of every capacitor you could possibly need. I think that that's really cheap insurance. So I just throw in a new capacitor. Yes, I do test capacitors sometimes, but by and large, I throw in a new one. Yes, sir?
Matter, you go one step up to the center
Now, that having been said, Sencor has an LC103 capacitor tester that's a really cosmic thing. It's expensive, but it really is it's a good thing. It's really a great tool. I can buy a hell of a lot of capacitors for $1,500 though. It's a different philosophy. I like Sencor. I love them. Their equipment is fantastic. I'm a cheap and dirty technician. I do a lot of my work in third world places, in hotel rooms and stuff like that. So I have a big bag of capacitors. All right. Now, this is one of them. Let's take a look. Actually, let's take a look at the actual schematic diagram here, and let me show you what I'm talking about. Go back to the Cortex schematic, the one with the deflection circuits on it, the one with the power supply on it. And in this monitor, the vertical deflection circuits are all the number 500s. And this is the vertical output chip that I showed you, the one that's mounted on the heat sink. This is it right here, this TDA8172. Okay. It seems kind of unusual that they drew it as a triangle because that's typically reserved for amplifiers. I guess it is an amplifier in a way because it takes the oscillator signal in and boosts it up. It's somewhat unusual to draw it as a, well, I guess now that I think about it, I guess it is an amplifier. Now, let's start with, let's start by first of all figuring out how you can figure out which is the vertical parts. The first time I looked at this schematic, the first time I looked at this monitor, I went, holy mackerel, what is all this stuff? Where I'm working on a vertical deflection failure, where are my vertical deflection parts? Here's how you figure this out on your own, and it's real easy. What I do is, the first thing I look for the yoke. So right kind of in the middle of the schematic right here is the coil that says V-dy, which is their way of saying vertical deflection yoke. It'll either say VDC, vertical deflection coil, it just might be labeled vertical yoke, vertical deflection yoke in this case. Let's follow it back and see where it came from. This is not where it's going, it's where it came from. Outputs are on the right-hand side. So if we go back to the left, we can see where it came from, and where it came from is IC501. So right away I know that since that's the coil, that must be the output device, correct? Because it's hooked right up to the coil, duh. And it also tells me that the vertical parts are the 500s. Right? So if you look all around here, C504, D501, they're all like the 500s. So let's see if we can find that capacitor there. So the output comes from this pin, pin 5, and it goes out this way to the right, goes through the vertical deflection coil, goes down. Well, there's that 2200 microfarad I was talking about, C507, and then it goes through just a very low ohm resistor, 1.8 ohms, kind of an unusual value, to ground. Right? So, I mean, that's how it works. The output comes out of this chip, goes through the deflection coil, through this capacitor, to ground. Well, since all of the yoke current has to go through this capacitor, when it fails, when its ESR increases, meaning it has more resistance, it doesn't allow enough current to go through, and the picture shrinks. If there's not enough yoke current, the picture isn't big enough, and the picture shrinks. Make sense? So that's one of them. Okay? Now, this is, wake up, man, wake up, wake up. I'm going to tell you something that's so critically important. This, what I'm about to tell you, solves the problem where this happens, and some of you have probably encountered this. You get to a monitor, you just have a horizontal line on the screen. You say to yourself, oh, I have bad vertical deflection. You do find that the vertical chip is bad because you replace it and you get your vertical deflection back. You go, yippee, I fixed it. And then 1 hour, 2 hours, 1 day, 1 week later, it fails again. And you say to yourself, wow, I must have gotten a defective chip. Let's replace it again. You replace it again, it works. Beautiful. And an hour later, or a day later, or a week later, it blows it out again. Look very carefully. On all of these schematics, you will see a capacitor, an electrolytic capacitor, connected between 2 pins of that integrated circuit. You see it right here as C504. That's a pretty typical value, 220 microfarads. Might be 100 in some cases, 220, 330, 220 is pretty typical at 35 volts. It's just a little capacitor that's physically located near the chip. In other words, without even having to verify it, the vertical output chip is here, got to be that one, which I'm sure it is. It's right near it. Now, here's what that capacitor is for. I know I'm running a little late for break. Just stand by. This is really important. You'll always see two pins connected with some sort of electrolytic. Let's call it what it is, 220 microfarads. This capacitor, This capacitor is known as the charge pump. It might also be called the boost capacitor. It might be referred to as I disagree with this. Ray, I'm going to run this by you. I disagree with this term, but I've seen it labeled flyback cap. Have you seen that, Ray? Never seen that labeled flyback cap? I understand why they might have called it that. I disagree with calling it that because typically in a monitor, when we talk about flyback, we're talking about the horizontal flyback transformer, the high voltage transformer. So it's called the charge pump or the boost cap or the pump up capacitor or whatever. And the way it's connected in the circuit, and you don't have to know all this, you just have to know it's a common failure item. It's kind of connected through a diode to the plus 24 volts DC that comes from the power supply. We saw the 24 volt output from the switch mode power supply, so you know what I'm talking about. It actually comes through a 1.2 ohm resistor from the switch mode power supply, the plus 26 volts, that's the SMPS, the switch mode power supply. Now here's what that is for, and I don't really care if you remember what it's for, you just have to know that it's a common failure item. It takes about 50 volts, 48, 50 volts to fill the screen from the top to the bottom. Our power supply is only half of that. Our power supply is only like 26 volts. The way this works, if you're interested, for those of you that are hotshots, is that the power supply comes in here and powers the chip. But at the same time, it also charges that capacitor. Then inside the chip, it takes that capacitor and puts it in series with the power supply. I have a 26 volt power supply, 24, 25, 26 volts. I have a capacitor that's charged up at the same rate. Now I have 50 volts is what I need for full deflection. So that's what it's for. When that capacitor fails, the picture starts to shrink because it doesn't have the full deflection voltage that it needs. Well, here's the insidious thing. Every time it starts to shrink, you're cranking up the height. Then it starts to shrink more because that capacitor is bad, and you crank up the height some more. As you're doing that, you're causing this vertical output chip to work really hard to compensate for the fact that we don't have the right voltage. It has to pump a bunch of current through the yoke to compensate for the fact that the original voltage isn't high enough anymore, and that's what blows that chip. It gets really, really hot, and it blows that chip. Never, ever, ever replace in my opinion, never replace a vertical output integrated circuit without replacing the charge pump or boost up capacitor or whatever it's called. It is 15 cents a cheap insurance, baby. It's really, don't test it at all. Don't worry about it. It's 15 cents. Take the thing out, throw it away, stick in a new one, put in the new vertical output chip, and you're done. Make sense? Okay? That's really, really important. Now, I have one more quick thing to talk about in the vertical section. Let's take a quick 10 minutes. I'm going to go over that, then we'll go over horizontal, and then we'll be done. So let's take really a quick 10 and come on back. All right, listen, I need to boogie on this because this is some real critical stuff that you just have to know. Going back to the vertical circuit, okay, this is really a critically important thing, easy to understand. We'll answer lots of your questions if you have them. We'll enable you to fix these things really easily in general. When you have a total loss of vertical deflection, just a horizontal line on the screen, the first thing you suspect is the vertical output chip. Before you rip the thing out and replace it, you need to make one quick power on test. It's one of the few tests you have to make with the power on other than the power supply itself. And that is to measure the voltage at the power pin of the chip. Whichever pin it comes in, it might be labeled V sub CC or VSS, or it might just be labeled power, something like that. You have to be able to measure the voltage at the power pin of the integrated circuit. That is really, really important because you want to see if you have the power there or not. Certainly, if you don't have the 24 volts or so that it always requires to operate these things, that would explain why you don't have any vertical deflection. Well, if we look at the actual schematic diagram here, you're hoping and praying that the 24 volts isn't there because that sure explains why I have no vertical deflection. If I don't have the voltage there, I certainly don't want to replace the chip yet until I figure out why I don't have the voltage. And almost invariably, in almost every monitor design I've ever seen, that 26 volts, which comes out of the power supply, which we already looked at, comes through a low ohm 1 or 2 watt resistor. Typically it's 1.2 ohms, typically 1 or 2 watts, before it goes into the chip. This resistor is kind of a protection device in a way. It's in this month's Slot Tech magazine. There's a discussion of inrush current, and it protects this thing called inrush from inrush current. And in a way, it kind of acts like a fuse as well. And this is where I'm going with this thing. Resistors, when they fail, either go up in resistance or open circuit completely. Typically, they open circuit completely. They can go up in ohms, but they never short. Resistors don't short circuit, they open circuit. Well, if that resistor is open, of course, that explains why I don't have any power to the chip. So you get to the monitor, you just have a horizontal line on the screen, you say to yourself, I have bad vertical deflection. You measure the voltage at pin 6, or whatever the pin happens to be, and you say, yippee, it's not there. Cool, that explains it. You can either, at this point, look at the schematic and go back to the power supply, or even just look at the power supply itself and measure the diodes and at the low ohm resistors, and say to yourself, either with the power on, gee, I don't have any voltage on that side of the resistor, but I do have my 26 volts on that side, so I assume the resistor is open. Or you can safely, with the power turned off, use your meter on ohms, simply locate that resistor and measure it and find that it's open. Is everybody okay on that? And that explains why you have no vertical deflection. So here's what happens. You go, okay, I have a horizontal line on the screen. Sure, easy. Power on. Pin 6, 26 volts is missing. Turn it off. Measure the resistor. Oh, it's open. Cool. You stick a new resistor in there, you fire it back up, and as soon as you fire it back up, that new resistor you just put in there smokes. And you go, oh, heck. Well, you probably say something more than that. But resistors typically don't smoke on their own. Resistors fail because something else has failed, drawing too much current across the resistor, and that's what's opened the resistor. And that thing is the vertical output chip. What these guys do when they fail, almost always, and I'll run this by Ray in just 1 second, in my personal experience, what these things do is basically short from the power to ground. Not a dead short, but something that draws a lot of current across the resistor. Ray, pretty much? Okay. And that's what opened the resistor to begin with. So, here's what you do. To prevent you from burning out the new resistor you just put in there, you do one of two things. You get to the monitor. I'm just going to repeat the whole process. Flat screen. Okay, no vertical deflection, not horizontal, not high voltage, not any of that stuff. Measure the voltage with the power on at this pin, the power pin. It's not there. Yippee. Measure the resistor. It's open. You replace the resistor, and when you go to fire it up again, put your finger on the resistor and then turn it on. And if it gets real hot real fast, woo, turn it off real fast before the resistor opens up. Or a more professional way to do that would be with the power turned off. You've just replaced the resistor, so the power's off anyway because you just soldered on it. Put your meter on the ohm scale and measure the ohms from ground, from pin 6, the power pin, to ground. In a normal working monitor, try this on a good monitor. It's thousands and thousands of ohms. If the chip is bad, that'll be 10 or 100 or something like that. It'll be something obviously way lower. And you say to yourself, woo, well, I'm not going to fire it up because if I do, it's just going to take the resistor out. By finding very low ohms from the power pin to ground with the power turned off, you've really verified that the chip itself is bad. Then you change the chip at the same time you've changed the resistor. You fire it back up. Ooh, let's remember to change the boost capacitor at the same time. You change all three of those things at once, and then it works. And what this avoids is this weird problem where people go, well, it's not a weird problem, it's common. No vertical deflection, so they just guess and change the output chip. That didn't fix it. Maybe eventually they figure out that they don't have power to it and they find that resistor open and they change that, but because the boost cap, which is the thing that caused it to fail to begin with, is bad, it fails again. It takes the resistor out and the new chip you just put in. So every 2 weeks you're sticking in a resistor and a chip, a resistor and a chip. And then, and then it's a vicious cycle and you never win. But by changing all three of these things at once, if required, then you're all set. That's a cool thing. That's a really important thing to know. The big clue here is that this thing shorts, the output chip shorts, and draws too much current across that resistor. But I've seen it again and again and again and again and again, where people bring a monitor into the class from the monitor lab, and we spend a couple of days on monitors just working on them in the class, has a flat line on the screen. I look at the board. He's obviously changed the vertical output chip. And then all that's left to do is change the boost cap and the resistor, and it works. So he really did find the bad part, but there was more than one bad part. That this part failing caused this part to fail, which then caused that part to fail. Just a chain of events. Okay, does that make sense? Okay, that's a really critically important thing to know about how the vertical circuit works. And in general, that's really typically what happens. I haven't ever seen this thing fail, so you can almost always assume, I hate to make those assumptions, but you can kind of in this case, that you do have the drive to the chip. It's really not going to be anything back this way. You can pretty much guess that it's going to be in the output circuit where your problem really exists. Okay? Okay. You should always have 1.2 ohm 2 watt resistors. They're real common failures. That's one other thing I wanted to mention now. Very important. If you read Vertically Challenged in last month's Slot Tech magazine, when the remote adjustments board is not plugged in properly, you also lose vertical deflection. If it's not plugged in at all, typically in most monitors, you don't have any vertical deflection, because typically if there is a vertical hold pot, it's on this board, and then the oscillator doesn't work because the vertical hold pot's not hooked up. Okay? All right, so that's the vertical circuit. I would ask for questions, but there's no time, so we'll move on. Well, I can't tell you how frustrating it is for me. Not that I'm not having fun. I am. I love doing this, but it's frustrating when I have to leave things unsaid. And I've left a bunch of stuff unsaid, but here we go. Look at the horizontal deflection circuit, and we're still on the same page as the vertical deflection circuit with the block diagram, whatever page that was. What is it, 37?
37.
Yeah. And here's a typical horizontal deflection circuit. Fortunately for us, the basic horizontal deflection circuit is more or less the same in every monitor. And also, fortunately for us, there is typically only one thing that typically fails in the horizontal deflection circuit. The horizontal deflection circuit begins with the horizontal sink. The horizontal deflection circuit begins with the horizontal sink signal, which we know comes from the computer board itself, and it triggers, in this case, the horizontal oscillator. And this is where the 31.5 kilohertz, if we're talking about a VGA monitor, is born in the horizontal oscillator. This is actually the same integrated circuit as the vertical oscillator. I don't even mean the same type. I mean the same exact chip. Since all monitors need a vertical oscillator and all monitors need a horizontal oscillator, they make one integrated circuit that is both the vertical and the horizontal in the same chip. Why have two different integrated circuits? If you're going to need both of those things anyway, might as well do it this way. It is, however, two completely separate integrated circuits in one package. They're not connected in any way. They even have this, other than ground, I guess, they even have two different power supplies. There's like a 12 volts that goes for the vertical, and there's another input that's That's plus 12 volts for the horizontal. Two completely separate power supply inputs. But it's one chip, and again, it's real reliable. The only time I've seen this fail is when I've caused it to fail or someone else has caused it to fail due to carelessness. Like that. So it's really the same. It's the TDA 9102 that I showed you before. I'm not going to show it to you again. And just as it was with the vertical circuit, if you are adjusting the horizontal hold control, which might be referred to as horizontal frequency in some monitors, you're adjusting that frequency, and you get it kind of in the ballpark, and the sync will come along and lock it in place, which we know doesn't work in this particular monitor. Okay. Now, the output of the oscillator is definitely not powerful enough to drive the deflection coil in the yoke, just like in the vertical deflection coil, the vertical deflection circuit, I should say. We end up having to drive the horizontal deflection coil in the deflection yoke, and it needs a lot of current to drive that. In addition, remember, the horizontal deflection circuit's also driving the high voltage unit, the flyback transformer. So there's no way that an oscillator is powerful enough to do that. So the output of the oscillator goes to a transistor called the horizontal drive transistor. And this is always an NPN transistor. And it actually drives the primary winding of what's called the horizontal drive transformer. It's just a tiny little transformer. I've repaired one once in 30 years, but other than that, it's just a transformer. A transformer is pretty much the most reliable component in existence. And so the chances are you won't have a bad horizontal drive transformer. This guy is connected through a resistor to one of two things. It either goes up to the B plus, or it goes up to like the plus 24 volts DC, typically, depending on the design. More and more modern designs are going with 24 volts here. All the older designs used to always be the B plus. But since switch mode power supplies have become common, very often it's the 24 volt power supply. Meaning that, remember the 24 volt power supply I just showed you, the switch mode power supply that has a resistor that comes out, the 1.2 ohm resistor, and then that goes to the vertical output chip. Everybody remember that from a whole 15 minutes ago. This is really important in a monitor like this. Try to remember this. Try to remember this. If the vertical output chip fails and shorts out, it opens that resistor. That's the plus 24 volt DC power supply, isn't it? That resistor's open now. There is no power to the horizontal drive circuit. The monitor is completely dead. Even though your original problem was loss of vertical deflection because the chip goes bad, your symptom in some cases in a monitor like this will be totally dead monitor, because you are missing the 24 volts that powers the primary side of this horizontal drive circuit right here. So it's an insidious chain of events. The chain of events is the boost capacitor has failed, let's say, taking out this chip, which takes out the resistor, which kills the high voltage and kills the horizontal circuit. So when you go through the power supply, when you're checking these voltages, if you could check on the other side of the resistor as opposed to that side, that's kind of an important clue, because you'll go, okay, I got my B plus, I got my 12 volts, ooh, my 24 volts is missing. Then you check that the resistor and you see that it's open. If I have my 12 volts and my B plus, all the power supply is really working, isn't it? The primary side's got to be good. We have some kind of a secondary problem, and the only thing it could really logically be is an open resistor. So the first time I encountered that, I thought, isn't that interesting? A vertical problem causes me to have no high voltage, no horizontal at all. Just be aware of that. It's a little more advanced kind of a thing. It's not terribly advanced. And after you've been working on monitors for a while, it's really a piece of cake. That having been said then, this transformer is a step-down transformer that steps the voltage down to about a volt, just 1 volt here. And the reason it's only 1 volt or so is that this transistor, this output is going to be driving the big wazoo, the hardest working transistor in showbiz, which only takes 0.7 of a volt to turn it on. This guy right here, the horizontal output transistor, referred to by some people as the HOT or the HOT. I personally don't like the term HOT. I don't know, it's a transistor. Let's call it what it is, the horizontal output transistor. But you'll talk to people all the time and you'll say, hey, I got a bad HOT, or the HOT is bad, or whatever, horizontal output transistor. And it only takes 0.7 of a volt to drive it, so that's all we need to come out of the transformer. About a volt or so will be plenty. The horizontal output transistor is an extremely common failure. It drives the primary winding of the flyback transformer, which is connected to the B+, not to the 24 volts, B+. And here's the high voltage transformer, better known as the flyback transformer, and you can kind of get an idea now of why it's called the flyback transformer. It's driven by the horizontal circuit. If you remember the way the horizontal circuit works, it makes the beam move from the left to the right, and then it quickly flies back to the left. Flyback transformer, it's driven by the same thing. The voltage builds up, and then it flies back down. So, called a flyback transformer. It's a little more than a flyback transformer. It's got some potentiometers and some diodes in it. Technically, its real name is Integrated High Voltage Transformer here in the United States, IHVT. Nobody will know what you're talking about if you call it that. If you don't call it the flyback, no one will know what you're talking about. But its technical term is IHVT. In Europe, they call it the LOPT, L-O-P-T, line output transformer. What line they're talking about, I got no idea, Ray, but that's what they call it. So anyway, so that's the flyback transformer. Well, the way this works is real simple. The oscillator drives the horizontal drive transistor, which drives the horizontal output transistor, which drives the flyback. This is a specialized transistor, teen guys and gals, very important. This transistor has a built-in diode, typically, not always, but typically, called the damper diode, D-A-M-P-E-R, the damper diode. If the transistor that came out has a damper diode in it, the transistor that goes back has to have a damper diode in it. That's really, really important. I never go nowhere without horizontal output transistors. This box is full of them. Horizontal output transistors, extremely common failure. When you test the horizontal output transistor, it does not test normally. It does not check like a normal transistor. And the reason it does not check like a normal transistor, you'd swear to God it was bad, even though it's perfectly good, is that A, it has this built-in damper diode. So when you check between collector and emitter, you will see the diode there. Forgive me, those of you that don't know electronics, how to test semiconductors. Junction drop one way, open the other. Between collector and emitter, you see that diode that's built into the transistor. But the thing that really throws you for a loop is it also has a low ohm resistor in it, typically between base and emitter. In circuit, this will always check shorted base to emitter. You don't have to bother checking it from base to emitter. It will always appear to be a dead short from base to emitter because of this small secondary winding here, which is just a few turns of wire. The emitter is grounded. So is this side of the transformer. When I check between base and emitter of the transistor in circuit, I'm really checking across just a little piece of wire here. So it always appears to be shorted in circuit. You don't have to bother checking it in circuit. But even if you take it out of circuit, it likewise does not check perfectly okay. Let me show you what I'm talking about. Naturally, you check diodes and transistors on the diode test setting of your meter. And again, if you don't know how to do this, you really need to learn it. So here's the transistor itself, and from the way the pins are on a transistor like this is called the TO218 package or the TO3P for plastic package. They're in alphabetical order from left to right. Base, the middle lead's the collector, the right-hand lead is the emitter. So if I were to check this transistor, you don't need to see me do it, I guess. Well, I guess I better show you. Hang on. if I check this transistor from base to emitter, even out of circuit, it appears to be bad. I'm not faking you out. You see how it says 0.05? Normally what you'd see between base and emitter is a reading like that, 0.4, 0.5. But between base and emitter, on a normal transistor, but in this transistor between base and emitter, it always seems to be almost dead short because of that resistor that's in there. That resistor is only about 45, 50 ohms. If I put this on the ohm scale, we can actually measure the resistor, 52 ohms. It's only 52 ohms. So that affects the reading. You don't have to bother with the base to emitter junction. And in fact, on these transistors, you only have to check it between collector and emitter. Between collector and emitter, the right-hand leg, the center leg to the right-hand leg, one direction it's open, the other direction you see that junction drop, which indicates the damper diode that's in there, that built-in damper diode. When these fail, they will dead short between collector and emitter. Dead short, and you'll get that. Dead short. They always do. I mean, just I've never seen one that didn't. All three legs might short together too. But there is a really fast way to test this. You don't have to do much to test the horizontal output transistor in a monitor. Since the emitter is always grounded, if I put my black meter lead on something on the chassis that I know is ground, like the grounded heatsink, I am connected to the emitter. I'm not sure how this is going to show up. Probably not at all. Come over here. Oops. Go back up. Go ahead. All right. If I connect the black meter lead to this grounded chassis, I am connected to the emitter, correct? Because the emitter is always grounded. This is always an NPN transistor with a grounded emitter. Then all I have to do is take my meter, set on diode test or continuity beeper or whatever, and somehow I have to touch the center leg of the horizontal output transistor. Well, the horizontal output transistor is always the largest transistor closest to the flyback. It's in a modern monitor, it's always in that package that I just showed you, the TO218, TO3P, whatever you want to call it, this little package right here. I mean, well, big package, really. I mean, that's what it always looks like. So all I have to do is touch the center leg. Now, in older monitors, there was a metal tab on the top, which was also the collector, which made our lives a lot easier. But modern transistors, they're typically in a completely plastic package. So I have to somehow get to the center leg. Well, it's kind of difficult to do, but if you're real careful and you can snake your meter probe down in there, and I guess I shouldn't have put the remote adjustments board back on. If I can get in there just perfect, there, and touch the center leg, it's beeping at me. That tells me that the horizontal output transistor is dead short. Dead short, it's bad. Everybody with me on that? Now, here's the easiest thing. The symptom, of course, the overwhelming original symptom will be that there'll be nothing on the screen, naturally. Naturally, if the horizontal output transistor is shorted, you won't have any high voltage and the screen will be blank. It won't blow the fuse, however. The symptom that you get when you have a bad horizontal output transistor, which this one is this. Now, I need you guys to be absolutely quiet here. Be absolutely quiet. No. Can you hear that real subtle ticking, like a ticking of a time bomb? It's real faint. It's real faint. Maybe you can't hear it. It's real faint. I was trying to mic it. I'm going to leave this thing ticking so that during lunch you can come up and listen to it. You will hear a subtle ticking like this. It sounds like this. That's all. That's what it sounds like. Or it will be making a chirping sound. It'll be going like beep, 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 like Ceronics does, and some others do as well. What you're hearing is overcurrent protection. Remember the switch mode power supply we were talking about before? Well, switch mode power supplies all have a built-in circuit known as OCP, overcurrent protection. And what the power supply does is this. If for some reason we have too much of a load on the power supply because the transistor has dead shorted to ground, so the B plus power supply is being dragged through the primary of the transformer right to ground, that would blow the FET in the power supply just like that. If I overload this thing, the power supply is just going to try to increase the duty cycle, and the transistor is going to work real hard, and it'll just fry the FET. Horizontal output transistor is extremely common failure. Wouldn't it be stupid to make a design where one of the most common failures in the world always causes something else to fail as well? That would be stupid. So they have this OCP, overcurrent protection circuit, that's built into the switch mode power supply. And what OCP does is this. When the horizontal output transistor fails, it short circuits and draws a lot of current, and the power supply shuts itself down. Well, about once a second, it kind of brings itself up and says, how you doing now? Are you okay? Oh, heck, you're shorted. How about now? Are you okay now? Oh, man, you're shorted. What about now? Are you still shorted? Oh, man, you're shorted. Well, every time it comes up in voltage and then goes back off again, it makes that ticking sound. And that ticking sound is coming from both the yellow transformer and the flyback transformer. They're just making this little sound like that. And if you hear that sound, what that's telling you is that it's gone into overcurrent protection due almost invariably to a shorted horizontal output transistor. Then all you have to do is turn it off, check between collector and emitter, beep, yes, it's shorted. Take the transistor out, put a new one in, and you're done. It doesn't change, doesn't blow the fuse, doesn't do any other damage. You just replace the horizontal output transistor, and it works. And that's all there is to it. That's why I always carry this. I think that this is an in-the-field repair. I mean, it only takes about 5 minutes to jerk a monitor out, take the board off like I've done here, 3 solder joints and 1 screw, and I got the thing out, put the new transistor in. Always screw it in first before you solder it in place, because otherwise the hole won't line up right. You'll do this wrong once, and you'll never do it wrong again. And then you're done. I mean, that's all there is to it. It's really, really, really simple. Does that make sense? Okay. It's a really cool and really simple thing. Now, I'm sure it must be noon already, but hang on. It's not quite? Oh, I got plenty of time. Super. Oh, let me relax a little bit. Does this make sense? Are you okay with this? Because this is a super common failure. I mean, I can't tell you how many times in the class someone brings in a monitor and it looks really dead. I mean, it is dead. And all I do is this. Okay, horizontal output transistor's bad. Next. I mean, that's a 0 diagnosis time thing. It really is. It's incredibly simple. And that's the deal. There are a number of different horizontal output transistors that exist, but quite frankly, they're fairly interchangeable. They're not totally interchangeable, and I have a few different part numbers that are horizontal output transistors. It's kind of like if I have a 19-inch monitor, I could take a horizontal output transistor from another 19-inch monitor of the same resolution, and it works, more or less. There's some exceptions to the rule, but I routinely just kind of try one. In other words, it's like, I got a bad HOT. Well, I don't know, try that one, see if it works. You know, and if it works for 10 minutes and then blows out, well, try that one, see if it works. Now, we did an article in Slot Tech magazine about horizontal output transistors and about the different frequency responses and the current ratings and all that kind of stuff. If you look through your old archive of Slot Tech magazine, I'm sure you'll see it. And it's really one of the best articles I've written. I think it came out really, really good. Anyway, so that's that. Do not confuse OCP with X-ray protection. This is really a common mistake that people make. X-ray protection is, remember, when the power supply goes over voltage, the monitor comes on for a split second and then turns off. That's X-ray protection. This is also protection, but it's not X-ray protection. It's overcurrent protection. X-ray protection shuts off the horizontal oscillator, actually. I can tell you now. I couldn't tell you before. What the X-ray protector actually does is shuts off the oscillator. And I'm actually not going to cover it. It's in the book if you're interested. But as long as you know that it exists, that's all I care about. And, of course, if the oscillator's dead, there's no high voltage. OCP shuts down the power supply. but it comes up again. It goes off, comes up, goes off, comes up, goes off, comes up. X-ray protection comes on and goes off once, and that's it. It just comes on and then goes right off, and that's all there is to it. Okay. Now, I realize now I actually have to do something else here. Yeah, every now and then somebody asks about firing up a monitor without a picture tube. Like if you don't have a CRT, can I just fire up the chassis by itself? Kasi si, kasi no. You can kind of do that, like to check the power supply and stuff like that if it's not working. But you have to be real careful. I don't like doing this, but some people do this. They'll take the second anode and put it inside a coffee mug or a baby food jar or something like that so that it's insulated, or at the very least, put it down on the bench and put something heavy, non-conductive over the top of it, because if the horizontal is working and the high voltage is working, you got 20,000 volts there. I highly don't recommend doing it. I've done it a few times. I don't recommend doing it. Some people do it all the time. If you do something safe for the second anode, you're probably okay. I would really highly unrecommend ever firing it up. But if someone gives you a chassis and you have to fix just the chassis for some psycho reason, you don't have anything to hook it up to, and you have a power supply problem or horizontal output problem or something, I mean, you could fix it and test it without the CRT. You can't see anything, obviously, to be sure that it's fixed, but depending on your failure, you might be able to do it that way. So that having been said, since I'm going to fire this thing up, I am going to hook up the second anode here just to keep things safe. I want to show you a really cool little trick here. And this is my final trick. And it's probably the trickiest of all, but it's really a cool trick. Now, this will either work or I will go up in a burst of flame and smoke. So let's see. I know that. I'm doing this without you seeing it first, and then I'll. Oh, come on. Oh, I don't have the yoke hooked up. Sorry. It'll be worth the wait. Just bear with me. Now it should work. Ooh, baby. I don't have the CRT ground hooked up. How come that's not working? I don't like that. Ooh, baby. Without the CRT ground hooked up, I've got all kinds of big, static charges. Remember I told you about the CRT ground and how it'll jump to you? That's what you just saw happen there, if you saw something happen.
Hey, I missed it. Show me again. Turn the camera on.
I will. I'm just hang on a sec. All right. When the monitor goes into X-ray protection, it comes on for a split second and goes off. If you know what you're listening for, you could hear that happen. If you know what you're listening for, it's pretty obvious. But in a loud environment, you'd never hear it. And if you don't really know what you're listening for, you can't interpret what you're hearing, really. It's important to know if you have high voltage in a monitor. Certainly, if you see anything on the screen, you know you have high voltage. But just because you don't see anything on the screen doesn't mean that you don't have high voltage. You might have a bad heater circuit. If the CRT heater, that the 6.3 volts is not there for some reason, you'll still have high voltage. You just won't see anything at all on the screen. So if you see something on the screen, it means that you do have high voltage. If you don't see anything on the screen, it does not mean that you don't have high voltage. Is everybody with me on the difference of those two things? Well, you can use a little device known as a neon lamp. This little thing is an Ne2 neon lamp. Lampara neon, a little neon lamp. And it has two electrodes, as you can see, and it has neon inside, neon gas. It's an Ne2 neon lamp. That's the part number, Ne2. It is the oldest component in existence, probably. I mean, this part's probably 100 years old. Well, not this exact one, but I mean, they've been making them for that long. Well, we can use this thing as a high voltage indicator. It's really pretty cool. All you have to do is hold the neon lamp against the flyback transformer, and it will glow orange. Typically, you hold it near the core of the flyback transformer, and it glows orange. If I hold it down here, it'll really glow. Can you see it glowing? Okay, I'm just holding it up against the body of the flyback transformer. So I'm holding it by both the leads. I'm not getting a shock. I'm just holding it right up against the core, or in some cases right against the body of the flyback transformer, but it always really works if you hold it right up against the core. So that tells me that I have high voltage, that it's on and it is continuous. When you have a problem with X-ray protection, what will happen is this. It'll just flash once. You hold the neon bulb up against the core with the monitor turned off. Then you turn the monitor on and watch the lamp. Okay, it came on and stayed on, right? So I know that I have high voltage, my horizontal is good, all that stuff is good. And I've got to kind of simulate this. When you have an X-ray protection problem, where it's gone into X-ray protection due to what failing? What section? Power supply. Power supply failure, right? Going too high in voltage, right? Here's what you'll see. It'll just blink, just like that. As the X-ray protector comes on, as the monitor comes on, and then it takes a split second for the X-ray protector to realize that we've got a problem and shut the monitor off. So you can get those at Radio Shack or MCM Electronics, any good electronics store. You can get them at any electronics store. They're like a quarter or 15 cents or something like that. They're pretty fragile. Get a few. You might break one. Hold the neon, with the power turned off, hold the neon bulb up against the core of the flyback transformer, energize the monitor. If it comes on and stays on, you don't have a high voltage problem, you don't have a horizontal problem, you really probably don't even have a power supply problem, because that powers the horizontal circuit, right? B plus powers the horizontal. It may not be perfect, but it's there anyway. On the other hand, if it comes on for a split second, it'll just go blink, it'll just go on and then off. That is telling you you're going into X-ray protection, not OCP. Not due to a shorter horizontal output transistor. It tells you you're going into X-ray protection due to some problem with the power supply, switch mode power supply, that has caused the voltage to go up too high. Make sense? Okay. I have a ton more stuff I'd like to cover on monitors. Monitors are really fun, but we're out of time. So that's my presentation on monitors. Thank you very much. I appreciate it. And let's eat lunch.
Probando.
When you do this, there are certain times in the demonstration when you're going to be having this thing on, and then certain times when you're going to be doing live stuff. Is that how it's going to work?
Oh, yeah.
You sure? Okay, because it's blinding. You want to be over here? Okay. That's fine. And then I can switch to that camera and show you the stuff, the stuff up close and personal.
Just don't fall asleep.
You wouldn't embarrass me by falling asleep in front of everybody.
I don't like tear hoppers,
Why not?
because when you get a jam, ammonia up to here.
Oh, it's heavy.
Yeah, plus, you know, to get it empty, to get this off, to get to the, it's like, it's a real pain to empty. And a lot of times the forepersons, they'll fill them, even though there's a little bit in there still, but it'll always just not fill it up.
Oh, to try to make it work.
Yeah.
To think that the weight of the coins, extra
Yeah.
coins, will somehow force it to work. Yeah, I don't know. You know, who teaches these fluorons anything? It's just
Yeah, I know.
unbelievable.
In a lot of the old Williams games, you can't even see the hopper really unless you look down the chute. But they do the same thing there. They don't know it's empty and they got empty cut. They boom. The hopper is actually full and they put another bag down.
Man, they must spill everywhere.
Yeah.
They must spill everywhere. Here, I'll give you a chance to go to either side. Oh, it's on. All right. So let me just go introduce Ray, and then I'll be right back. Stand by.
Yeah, I told him jokingly yesterday, I said, yeah, Ray's real nice gentleman. He said, he come in. There's a girl over there, isn't there?
funny. You know, half the people are over there, half are over here. That's a good deal. How many of you heard of Money Controls? Heard of them? Pretty okay, great. You know, it's funny. They don't have a giant market share here. They are really a UK-based company. Over in Europe, they're huge, gigantic. Over there in Europe, they're really just gigantic, pretty much. They're all over the place in Europe. But some people are a little less familiar with their stuff over here. They make all kinds of products, actually. They even make a ticket printer called Paycheck. I don't know, but you guys really don't sell it here at all, do you? I mean, you really just haven't done anything with it. But one thing that they do have is a coin comparator type of coin validator, let's call it, what they call Condor, and a really sweet little hopper that they call the Gamesman hopper. The thing just comes apart so easily, and it's a really good product. So this is his first time presenting at TechFest, so be gentle, everybody. Be nice to Cesar Niera.
Okay, as Randy said, my name is Cesar Nira. I'm the senior bench technician at Money Controls here in Las Vegas. Today I'm going to go ahead and talk about our Gamesman hopper, and I'm going to touch on our Paycheck, and I'm also going to talk about our Condor Plus, which, as Randy said, is our coin validator. I'll go ahead and pass this one around, and you can kind of take a look at it. I know you're kind of far, so I'll get up. All right, well, let's get started. First, we're going to go ahead and talk about our Condor Plus. It's a great unit, very user-friendly. It has serial diagnostics, which can be, it has to be turned on by us when the unit is ordered. What that allows is at power up, it runs a series